Hello, this is Jack Jackson. In our last video, we looked at a theorem called Rolle's theorem. That's something that works for for differentiable functions. And the mean value theorem is a generalization of Rolle's theorem. In Rolle's theorem, we required the function to be at the same heights at the ends of the interval, and then asserted that under the hypothesis of the theorem, there was a place where the function had a zero derivative. Okay. And of course that turns out to be the same as the slope of the secant line between endpoints of the interval, because we made sure the endpoints of the interval had the same height. And so in the mean value theorem, we're going to generalize this because we're not going to require the function to be the same height at both ends of the interval. But then we conclude there's a place in the interval not necessarily where the slope is zero, but where the slope of the tangent line is the same as the slope of the secant line. Remember that this relates to something we did way back when we did our unit on the meaning of the derivative. We approximated the derivative at a point with a symmetric difference quotient. Of course, that created an interval where the point we were interested in was exactly in the middle horizontally, and we had those two endpoints of the interval and made a secant line and did the slope of that secant line and used that to approximate the slope, right at the point we were interested in, which was right in the middle. Well, what the mean value theorem says is it's going to say that there is a point where that slope of that tangent line, that is the derivative of the function, is exactly equal to that symmetric difference quotient, or to that slope of that secant line. Okay, but it may not be exactly right in the middle midpoint of the interval. Okay, for some functions it is, like quadratics, it would be exactly in the middle, but there may be some other functions where it might be closer to one end or closer to the other. And there might be some functions where it happens more than once, but there's at least always one such thing. The mean value theorem was first published by the French mathematician Joseph Louis Lagrange, and Lagrange is famous for doing several important things in calculus. He was of that same generation with some of the Bernoullis. In fact, he did, or maybe just a little bit after them. He studied with Euler, who was one of the most prolific mathematicians of all time, who studied with the Bernoullis. So he is very important in the development and application of calculus. So an early father of calculus, along with some of the other folks we've been studying. So here's the actual statement of the mean values theorem. So let f be a function such that it's continuous on the interval a to b, closed interval a to b, and it's differentiable on the open interval a to b. Okay, then there exists a number c in the open interval a to b such that f prime of c is f of b minus f of a over b minus a. And you could recognize that as the slope of the secant line, and of course f prime of c is the slope of a tangent line. Okay, so notice it is a generalization of Rolle's theorem, and so what we mean there, for example, if f of b actually equals f of a, which is the third condition in Rolle's theorem, the Rolle's theorem has the same first two conditions here. Okay, but then it also has a third condition, that f of b equals f of a. If that third condition is satisfied, notice that f of b minus f of a is 0. B and a are not 0. B minus a is not 0. So this whole slope here is just 0, and that's the conclusion of the Rolle's theorem. So in one sense, if you got the mean value theorem, you automatically have Rolle's theorem. But in fact, in proving this, we're going to use Rolle's theorem to prove the mean value theorem. So the mean value theorem is a generalization. So let's look at a proof here. And really the proof is pretty straightforward. What we're going to do is let's just show you here. We're going to take a function f and satisfies those conditions, that it's continuous on a closed interval AB and differentiable on open interval AB. And of course that makes its endpoints a f of a and b f of b. And then we take the equation of the secant line through those 2 points. So just the equation of the line through those 2 points. Well, the slope then is going to be f of b minus f of a over b minus a. That's just your basic slope formula. So it's the slope times x minus a plus f of a. So that's just the point slope formula of a line, and I'll call that s of a, use s for secant line. So there's our function y equals that, or s of x equals that. Now what we're going to do, that's the equation of the secant line, and then we have our original function f of x. We're going to subtract them to find the difference between them. And this new difference function I'm going to call capital D of x is just f of x minus s of x. So that's f of x minus parentheses there. I'm going to distribute the minus. Let's see, that makes minus f of a, which I'm going to scoot over here next to the f of x. So I've got f of x minus f of a, and I've got minus that slope there, f of b minus f of a over b minus a, minus out front, and then have x minus a here. So that's our difference of the original function and its secant line. Now what we want to do is apply Rolle's theorem to this function d. So first we need to verify that the three conditions of Rolle's theorem actually apply. Well, first of all, since f is continuous on the interval a to b, closed interval, and of course linear function, s is a linear function, it's continuous everywhere, right? So that means certainly it's continuous on the interval a to b, and if you sum or difference two functions which are continuous on an interval, then the resulting function is continuous on that interval. Similarly, if f is given to be differentiable on the open interval a to b, and of course linear functions, again, linear functions are differentiable everywhere, so the function d is again differentiable, since the difference of two differentiable functions is differentiable. Now we just got to make sure that the f of a and f of b are the same. And so let's see, what's d of a, not f of a and f of b, but d of a and d of b. So d of a is f of a minus f of x, but x is a here, and then that's a constant there, and then we have a minus a here. Well, a minus a is 0, so 0 times this part gives you 0 here, and then f of a minus f of a is 0, so you get 0 for that one. Well, d of b is also 0. D of b is f of b minus f of a. So it's f of x minus f of a. So put the a, I should have said put the a in place of x here. That one was already f of a. So put the b in place of x here and here. Okay, let's see what we get here. Okay, look at this last part here. B minus a over b minus a cancels. And so then we have a minus here, which we're going to distribute. So that makes minus f of b plus f of a here. And we still have these first two terms. But then these terms cancel out. That f of b and that minus f of b cancel. This f of a and that minus f of a cancel, and you get 0. So d of a equals d of b, which equals 0. So we have the three conditions satisfied for Rolle's theorem. And so then the conclusion of Rolle's theorem says there is at least one number c in this open interval from a to b, such that the derivative is 0. It'll be a maximum or a minimum. Okay? Now, we're going to use the derivative shortcut rules to find the derivative of d, set it equal to 0, solve for f prime of x, and that should give us our desired result. So pretty straightforward here. Here's the formula for d of x. Take the derivative. First of all, we've got 1, 2, 3 terms, so we use the sum rule first to the derivative of each part. The derivative of f of x is f prime of x. F of a is a constant, so that's derivative is 0. This is a linear function whose slope is right here, so this right here is its derivative, like that. So, of course, you can drop the 0. So we're down to this point here. Then we set d prime of x equal to 0, so we put 0 here, and it equals this part right here. So we're down to this expression right here. So if we add the f of b minus f of a over b minus a, that's f prime to both sides of x. We get f prime of x by itself. And sure enough, that's exactly what we wanted to prove, that the slope of the tangent line f prime of x, I'm sorry, I should say, we'll do a slight thing. This is not true in general for any x, it's true for c. So d prime of c is 0, so when you put a c here you get 0, and a c here you get the result. So for that particular c value, we have the slope of the tangent line is equal to the slope of the secant line. And that completes the proof of the mean value theorem. Now let's take a look at the graph here. So I've got this illustrated with a purple graph here, a blue graph, that's the original f of x. And it's defined from a to b. In this case, I guess a is 1 and b is 5. So we've got a graph here. Notice that it's continuous on that interval. In fact, it's even differentiable on that interval. Continuous at the endpoints and differentiable in the middle of that interval. Then we make its secant line, which is this green line segment. Okay? And then we take that line segment and we find its slope. Okay? And it turns out there's a point here which has the same slope. Now, where is this going to occur? Well, first of all, we did the difference in these two. So we did the blue curve minus the green one, gave us this purple graph down here, d of x. Okay? And so at any point here, the height here, like given by this pink line segment, is the same as the distance between the two here. So if we went over here, for example, we'd have a smaller distance, which is illustrated by the corresponding smaller distance here. And of course, it gets to be 0 at both ends, which we saw algebraically earlier, and we see it graphed here. Well, Rolle's theorem says, okay, if this is the same on both ends, then there's some place in the middle where we have a slope of 0 going across, and a max or min, basically. And so a maximum or minimum, and that gives us the slope of the tangent line is 0, so horizontal tangent line. That happens right here. There's our c value, it's 3 in this case. So for that same c value, we go up here and draw the tangent line to the original curve, and notice that it has the same slope as the green line. So there's a place where these are the same. Now in this particular case, this is a quadratic function I used, so the place is going to be exactly halfway between the two endpoints where that happens. And in fact, that symmetric difference quotient that we get from here to here, it would actually be a symmetric difference quotient for this point in the middle. But on some other functions, this point may be closer to this endpoint or closer to that endpoint. Okay, so I think we went over everything I'm saying there. And so we're going to generalize this once again in the next video to something called Cauchy's mean value theorem.